If you're tracking, you should have obtained the following results. Even though source voltage spans the same peak-to-peak value of 6.8 divisions as our previous example, note we're using a different vertical sensitivity in this example of 10 volts per division. Given this vertical scaling of 10 volts per division, it looks like source voltage has a peak-to-peak value of roughly 68 volts. A 68 volt peak-to-peak value has a 34 volt peak value. A 34 volt peak value corresponds to an effective or RMS value of approximately 24 volts. It looks like the source voltage zero crossings going positive are separated by approximately 7.2 divisions. At 1 millisecond per division, this represents a period of approximately 7.2 milliseconds. A period of 7.2 milliseconds presents a frequency of approximately 138.9 Hz. Source voltage expressed as a phasor equivalent would be 24 volts at an angle of 0 degrees, where the phasor magnitude is the RMS value of 24 volts and a phase shift of 0 degrees implies 8 is the reference and all other properties will be measured with respect to this value. Let's now do the same thing for current data on channel 2 in blue. Channel 2 is employing a vertical sensitivity of 0.1 or 100 milliamperes per division. Channel 2 is also using a horizontal sensitivity of 1 millisecond per division. See if you can determine the current peak-to-peak value, the current peak value, the current RMS value, and the phase shift of current with respect to source voltage. Once you've got these properties, put current in phasor format. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given a vertical scaling of 0.1 amps per division or 100 milliamperes per division, it looks like current has a peak-to-peak value of roughly 500 milliamperes. A 500 milliampere peak-to-peak value corresponds to a peak value of 250 milliamperes. A 250 milliampere peak value corresponds to an effective or RMS value of approximately 176.8 milliamperes. It looks like current on channel 2 is lagging source voltage by approximately 0.7 divisions. At 1 milliseconds per division, this represents a lag of approximately 0.7 milliseconds. A delay of 0.7 milliseconds for a 7.2 millisecond period represents a phase shift of approximately negative 35 degrees. Source current expressed as a phasor equivalent would be 176.8 milliamperes at an angle of negative 35 degrees, where the phasor magnitude is the RMS value and a phase shift of negative 35 degrees implies it lagged source voltage by this amount. Let's now manipulate this phasor data for voltage and current using Ohm's law. See if you can determine the total impedance for this circuit in polar format. Once you've got total impedance in polar format, resolve it into rectangular format. Once you've got total impedance in rectangular format, determine the component level for the two impedances comprising this unknown impedance. Again, component level values. We're looking for the exact components that will exhibit these same properties at this particular excitation frequency, in this case 138.9 Hz. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. An application of Ohm's law demonstrates total impedance is 136 ohms at an angle of 35 degrees. Converting this into rectangular format yields a total impedance of 111.4 plus J 78, where the real component is the resistive component and the imaginary component is the reactive inductive component at this excitation frequency of 138.9 Hz. Why is this an inductor and not a capacitor? Because current in this example is lagging voltage. That is a dead giveaway. Current lags voltage for inductive elements. Additionally, total impedance in phasor format has a positive angle, and a rectangular format has a positive imaginary component. This is a clear indicator that the unknown reactive component is inductive in nature. The resistive component is undoubtedly 111.4 ohms. An algebraic manipulation of the inductive complex impedance formula suggests an 89.4 millihenry inductor would yield the desired reactive component at the given excitation frequency. Let's try one more illustrated example. For our final illustrated example, we are again presented with an unknown impedance having both resistive and reactive components. We're presented with the following data on an oscilloscope screen. Yes, this is a different style oscilloscope, yet it's still displaying the same data in a similar format. Do not screw this up just because it's a different color. That is a stupid excuse. Channel 1 in yellow is measuring source voltage. Channel 2 in blue is measuring source current. Let's concern ourselves solely with channel 1 source voltage in yellow for now. Channel 1 is employing a vertical sensitivity of 2 volts per division. Channel 1 is employing a horizontal sensitivity of 2.5 milliseconds per division. See if you can determine source voltage peak-to-peak value, source voltage peak value, source voltage effective or RMS value, the period, and the frequency of the source voltage. Once you've got this data, place source voltage in phasor format, assuming source voltage is the reference. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. You'll note source voltage in this example isn't perfectly symmetric because the positive peaks are ever so slightly smaller than the negative peaks. This being said, it's not that bad of a difference. Given a vertical scaling of 2 volts per division, it looks like source voltage has a peak-to-peak value of roughly 11.8 volts. An 11.8 volt peak-to-peak value corresponds to a peak value of approximately 5.9 volts. A 5.9 volt peak value corresponds to an effective or RMS value of approximately 4.2 volts. It looks like the source voltage zero crossings going positive are separated by 5 divisions. At 2.5 milliseconds per division, this represents a period of approximately 12.5 milliseconds. A 12.5 millisecond period corresponds to a frequency of 80 Hz. Source voltage expressed as a phasor equivalent will be 4.2 volts at an angle of 0 degrees, where the phasor magnitude is the RMS value of 4.2 volts, and a phase shift of 0 degrees implies source voltage is the reference and all other properties will be measured with respect to this value. Let's now do the same thing for current data on channel 2 in blue. Channel 2 is employing a vertical sensitivity of 10 milliamperes per division. Channel 2 is also employing a horizontal sensitivity of 2.5 milliseconds per division. See if you can determine the current peak-to-peak value, the current peak value, the current effective or RMS value, and the phase shift of current with respect to source voltage. Once you've got these properties, put current in phasor format. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given a vertical scaling of 10 milliamperes per division, it looks like current has a peak-to-peak value of roughly 52 milliamperes. A 52 milliampere peak-to-peak value corresponds to a peak value of approximately 26 milliamperes. A 26 milliampere peak value corresponds to an effective or RMS value of approximately 18.4 milliamperes. It looks like current on channel 2 leads voltage on channel 1 by roughly 0.8 divisions. At 2.5 milliseconds per division, this represents a lead of approximately 2 milliseconds. A jump start of 2 milliseconds for a waveform that repeats itself every 12.5 milliseconds represents an angular phase shift of approximately 57.6 degrees. Current expressed as a phasor equivalent would be 18.4 milliamperes at an angle of positive 57.6 degrees, where the phasor magnitude is the RMS value and a phase shift of positive 57.6 degrees implies source current leads source voltage by this amount. The measure utility on this particular oscilloscope allows us to display automated RMS, frequency, and phase shift measurements for the desired properties. Automated measurements confirm our manual measurements to a reasonable degree of accuracy. Let's now manipulate phasor data for voltage and current using Ohm's law. See if you can determine the total impedance for this circuit. Once you've got total impedance in polar format, resolve into rectangular format. Once you've got total impedance in rectangular format, determine the component level for the 2 impedances comprising the circuit. Again, component level values. We're looking for the exact components that will exhibit these same properties at this particular excitation frequency. In this case, 80 Hz. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. An application of Ohm's law demonstrates total impedance is 226.9 ohms at an angle of negative 57.6 degrees. Converted this into rectangular format yields a total impedance of 121.6 minus J191.6, where the real component is the resistive component and the imaginary component is the reactive capacitive component at an excitation frequency of 80 Hz. Why is it capacitive and not inductive? Because current for this example is leading source voltage. That is a dead giveaway. Current leads voltage for a capacitive network. Additionally, total impedance in phasor format has a negative angle, and a rectangular format has a negative imaginary component. These are yet more clear indicators that the unknown reactive element is capacitive in nature. The resistor is undoubtedly 121.6 ohms. An algebraic manipulation of the capacitive complex impedance formula suggests a 10.4 microfarad capacitor would yield the desired reactive component at the given excitation frequency. Alright, that's enough for today. Again, I must remind you that these techniques represent a mandatory minimum level competency that you will be expected to reliably demonstrate on a regular basis. You simply must be able to interpret sinusoidal properties from an oscilloscope display, place sinusoidal properties in phasor format, and use AC Ohm's law. If you need to revisit or review any of these topics, that option is available and encouraged. In conclusion, this lecture looked at a handful of illustrated examples that reviewed oscilloscope data interpretation, sinusoidal properties, phasors and phasor math, complex impedance calculations, and AC Ohm's law. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.